This video is testing the difference between means with small and independent samples. Now the criteria is similar to the large samples. Must be randomly selected, they must be independent, and then the third case, which is not true for the other one, is they must have a normal distribution because, as we've learned before, based on the central limit theorem, large samples, the sample mean is implied to be normal or approximately normal. But these populations must come from normal distributions. Now, one thing that's very important is there's two methods to consider when you are applying this two-sample t-test for the difference between two means. You can have what's called where the variances are assumed equal or they are assumed to be unequal. Now I'm going to go under the assumption they're going to be equal. And as I mentioned over here, there's a different method for calculating for the standard error, the degrees of freedom. One reason, the main reason I'm going to go ahead and go with equal is because the degrees of freedom is very tricky for the unequal, and I've seen it kind of computed different ways, and if you're going to use the technology in the TI-83, it's not going to match often, and it runs into some problems. But if we go with equal variances between the two populations, then the degrees of freedom and everything matches up pretty well, whether you're using the formula to do it or the calculator. So that's the main reason. But I wanted to make you aware that it exists and that is a possible scenario in the real world of statistics, at least anyway. All right, well, let's look at the formula for the t-test. Now, the way we set up hypothesis test is exactly like we did for large samples, so we don't need to go back through the basics of that, where you have mu1 equals mu2, mu1 less than mu2, all that stuff. We'll be using that, of course, but we don't need to redefine that. You can go back and look at that in the section for large samples if you'd like. Now look at the formula, very similar. Now, it's the x1 bar minus the x2 bar. Now, one thing I'll do here, I'll make a note of this now, like this was in the last section, where I have this crossed out. That doesn't look very good without using a stylus. And I'll try to put a little zero there. Well, that's not very good either, but I'll fix that. We're going to treat that as zero. In other words, just like the section for large samples, we're not going to worry about a specific difference between the two means. Or, in other words, if the means are different, we don't care if it's different by 5, just are they different? So we'll go with that same assumption. Now, like I said a few minutes ago, based on the right side is the equal variances. We're going to have what's called a pooled estimate of the standard deviation. Now, in this formula, the denominator is a little more complicated than it was for the last section. It's kind of messy, so that's why, come down here. First thing we have is this standard deviation with a little hat above it, that little caret above it. That's called our pooled estimate of the standard deviation. It's just the whole thing on the bottom's kind of messy, but it's not that hard to calculate. So if you look underneath, it's all under a square root here. So you take n1, your first sample size, minus 1 times the standard deviation squared, which of course is the variance of the sample standard deviation, plus the second sample size minus 1 times the second standard deviation squared. And then all that's divided by n1 plus n2 minus 2, and that's all under the square root. So then you got to do one more thing, though, to get this value in the denominator. I've sometimes seen people stop and think that radical is the entire denominator, but it's not. See, if you look, the sigma hat is right down there where I have it, and you see it's times something else. So you take this big square root, get a result, and then you multiply it by this other smaller square root, which is just 1 over n1 plus 1 over n2. all under that square root. You multiply those two square roots together, and that gets you your denominator for the test statistic t. And if you know, since we're using small samples, that brings back the idea of degrees of freedom that we've had with one sample t-test. And the degrees of freedom is calculated as n1 plus n2 minus 2. Basically, the idea of subtracting 2 is because we have two independent variables versus just one. Where before we just had n minus 1 when it was one variable. Now add them together, subtract 2. Okay, so it's a messy denominator in that t-test. Now, as I clipped out from the book here, this is very important if you're using the calculator because it's designed to do it both ways, whether they are equal or unequal variances. And since we're going to stick with equal variances, like I said earlier, that's the option you'll see when we do this in the calculator. When you see pooled, you will always choose yes in our world here. In another world, somebody might want to do it both ways. We like to talk about the calculations end up being off, and because the degrees of freedom is very tricky. It's not as easy as n1 plus n2 minus 1. All right, well, here's a problem we'll just kind of look at here. Let's see if I got from the book. This has to do with calling range for cordless telephones. And we are saying that manufacturer claims that its calling range is greater than that of the competitor. So we'll use the data given as the manufacturer being, and it's printed that way too. Same logic we've used with large samples. Whatever we see first, we'll treat as group 1, and whatever we see second, we'll see as treat as group 2. So here you see the hypothesis statement pairs here. They're claiming that they are greater than their competitors. So mu1 greater than mu2. Therefore, that makes the null, of course, mu1 less than or equal to mu2. So let's look at the data over here in the box. So we have a sample mean for the manufacturer 1275 with a standard deviation of 45, and there's a sample size of 14 phones for that group. The competitor 1250 was their range. 30 feet was a standard deviation, and we took a sample of 16 of their phones. All right. So you come over here. Now, before the calculation, they go ahead and mention the decision rule, which I'll take a look at that right now too. So you see variances are equal. We're choosing pooled, and the degrees of freedom is going to be n1 plus n2 minus 2. So it'd be 14 plus 16 minus 2 is 28. And we have a right-tailed test greater than 28 degrees of freedom. The alpha in this problem, here it is back up here, is 0.05. So remember, this is where we have to be careful whether we choose one tail or two tail. So it's one tail, 0.05. So it's the third column, 28 degrees of freedom. And there it is, 1.701. So then our rejection rule, or decision rule, is we would reject if our test statistic t ends up being greater than 1.701. So now what we have to do is calculate that test statistic and see if it is indeed greater. All right, so here's the process of getting that denominator. It looks like they're working on that first and then just bring it back in because the numerator really isn't too involved. So you see, look at so that sample standard deviation of the difference of those two means is they put the two radicals multiplied together. So you do that in as many steps as you feel comfortable. I'd probably recommend doing little by little, and don't round too much along the way. Keep enough. If you do the radicals separately, I'd probably use 4 decimal places each, and then 4 decimal places like they did here in this answer. So 13 is n minus 1, 14 minus 1, times 45 squared. That was the standard deviation for the group 1. N2 was 16, so 16 minus 1 is 15, times that standard deviation, 30 squared, all over 14 plus 16 minus 2, times 1 over N1, 1 over 14, plus 1 over 16. So you put all that in the calculator, and you come up with 13.8018. So that's the hard part of this. So now our test statistic will be the difference of two means with x1 going first. So the x1 bar is 1275 minus 1250 divided by 13.8018 that we got from over here. All right, so we get 1.811. Therefore, we would say that 1.811, since that's greater than 1. You see right here, 1.811, that's greater than 1.701, so we would reject the null hypothesis and we would support the claim that the manufacturer's cordless range is greater than its competitor. All right, so that's all there is to it here. Why don't we try this? Okay, let me show you this one. I'll just work this one out in the calculator. Looks like I didn't put the output. I'm sure I've got a calculator problem worked out somewhere down here coming up. Let me just check and see. If not, I'll add some in there. So, yeah, there's a little bit. Yeah, there's 2 samples, z-test. But let's go ahead and do it for this one. And I probably won't paste it in the notes. I'll just leave it here. If you watch the video, then you can see it. So we need stat, test, 2 sample t-test. Like so. Okay, we're inputting stats. Means we're typing in all the values. And don't know if I can. I'm going to try to take a guess on some of these and go double check. I think this one's 1275, or at least guess on my memory. I want to say 45. These I know. N1 is 14. I think this is 1250. Second standard deviation, 35. I think my memory's off on these. I'm going to go 16. But before I go any further, let me go back to the notes. Oh, 45 and 30. Okay, that was fairly close. Change that to 30. Have to pick the right alternative. Ours was a right-tailed, greater than. So we would select that. And like I say, we are always choosing pooled yes, because in our world, we're going to do it that way every time. Meaning variances are equal. We don't care about that. Calculate. Let's see what happens. And I don't know what else they show. This looks like they spit back. Let me scroll down for a minute and come back up here. They have the pooled standard deviation at 37.7. Well, there's the correct test statistic for T, 1.811. There's a p-value there, but like we learned for one variable for T, you're not required to get the p-value because it requires technology, and someone just using a regular calculator would be at a disadvantage. But if you're for Z, you're not at a disadvantage because you can, as long as you know the process, you can get it off the normal curve. Here, you would be at a disadvantage without the calculator. 1.811, so let's go back up here. I'm not sure what that 37.7 number was. You see this 13.18018. Unless that is the first part in the calculator without multiplying by the second part. I think I'll check that just for a second here. I'm not going to dwell on this if that's not right. I'm going to go 37. Oh, it went away on me. I think it was 713, something like that. Oh, I don't know if that would have rounded to 4 or not. I don't remember. Don't worry, you're not going to have to do this. I'm just checking out of curiosity. And then I want to multiply it by 1 over 14. The square root of 1 over 14. Okay, so that's what it was. That's what that number is in the calculator. You see, it's giving you the, so the final answer was right. It's just, that label is just for the big part of the square root without multiplying it by the other part. But not to worry, because you would ultimately then be looking for the final t result here, the 1.811. You would not need that. All right, so let's scroll down here. Manufacturer claims that the watt usage of its 17-inch flat panel monitors is less than that of its leading competitor. Okay, so keep in mind here, sometimes I know students don't like that when they use numbers as descriptor terms. It looks like the 17 might actually mean something in the problem. They could have used pink flat panel monitors. In that case, the 17 is not a numerical value in the sense of more of a descriptor of the item, but I know students can kind of get frustrated when they see too many numbers in a problem, but that's not a number involved in the calculation. So we're going to say, what are they, is less than that of its leading competitor. So they're claiming they're using less wattage. So we're going to have a left tail test this time. Alpha's 0.10, and we're assuming the population variances are equal. So I kind of, picked around in that section of the book because some of the problems do say if they are not equal, using that other method. So that will not happen to you. That's not on the exam review. Would not be on the test. So if you were just happened to be looking at the book, and I think any problems I would have put on a practice list, I would have made sure, unless I made a mistake, always let me know if you think something's wrong. But if you're just kind of going through the book, unless you're just curious, but don't worry about anything that says where the variances are not equal, because it'll be done that other way. So you probably should just avoid looking at those unless you've mastered this and are just curious. So here's the data. I'm not going to read all that here. I'm not going to say all of it. We're looking right at it for the manufacturer and the competitor. So the manufacturer will be group 1, the competitor will be group 2. And there's my null and alternative. It's a left tail test. They're claiming that their watt usage is less than. So therefore that makes the null be greater than or equal to. So you see I calculated the degrees of freedom here. N1 plus N2 minus 2. That'll be 25 degrees of freedom. If the degrees of freedom turned out being more than 29, which I generally avoid that, you can use that infinity row at the bottom, but I usually make sure they stay under 30 anyway. But just to let you know that. So we have 25 degrees of freedom. And alpha was 0.10, so this is, let's go to the chart. So 0.10, one-tailed test again. So it's the second column, one-tailed, 25 degrees of freedom. So it's 1.316, but remember, just like we did for one sample, t-test, the t-chart still works the same way. Left-tailed test, it's negative. You have to put the negative there. Once again, right tail is positive, and then two-tail automatically implies a plus and a minus. So keep in mind that does make it negative. So you see, here's my rejection rule, is reject the null if t is less than negative 1.316. sometimes negative numbers can get tricky. So if you want to use the absolute value, it's kind of like using symmetry of the curve. You can look at it from the same argument as when you calculate your test statistic and make it positive, and then if that positive is greater than this one, 1.316 made it into a positive, then that's also reject. It's just kind of mirroring it over to the other side, because I think sometimes students might be easier to deal with positive numbers than negative numbers. All right, so then there's the sigma hat part of the denominator. It's not the entire denominator, but so you see it's the n1 minus 1, 12 minus 1 times the standard deviation, all coming from, shrink this down a little bit. Everything's in the box. See the 2.1 standard deviation squared, plus the second n, which is 15, minus 1, times that standard deviation, 1.8 squared. All that's divided by the degrees of freedom, 12 plus 15 minus 2. And all that mess concocted is 1.9377. But once again, that's not the entire denominator. To get this standard deviation of the difference of x1 bar and x2 bar, we got to take that number we just got, 1.9377, and then multiply it by the square root of 1 over 12 plus 1 over 15. That comes out to be about 0.75. Now, that's our denominator. So you take the first mean, which was 32, see that in the box, minus the second mean, which is 35, divided by 0.75. That comes out to be like negative 4.00. Comes out to be negative 4 exactly. So since negative 4.00 is less than negative 1.316, or you see I flipped it over like I was explaining earlier there. If you want to flip it and look at it from a positive standpoint, you can. But it's in the rejection region, so you would absolutely reject. So here's just a little statement in words indicating our result. We would say there's sufficient evidence to support the claim that the watt usage is less than that of the competitors. And I think I'll go ahead and just put this one in the calculator real quick. And let's see, so it's stat, test, 2 sample t-test. Now this one I don't have memorized at all here. 32, 2.1, and 12. There's those 3. Next one's 35, 1.8, and 15. And then this is a left tail test. So we choose our alternative for a left tail test. There it is. There's our standard pooled yes. Don't care about that. Calculate. And the test statistic, negative 3.997. What did we have? Negative 4.00. Yeah, I think that's pretty darn close. So yeah, that's right on the money. So there it is. So please feel free to get your test statistic that way if you like. All right, so that worked. All right, so here what we have, let's see. Determining the salaries from elementary school teachers, 2 districts are equal. So they're taking 15 teachers from each district. The mean from the first district is 28,900 with standard deviation of 2,300, and then the mean from the second was 30,300 with a standard deviation of 2,100. Test the claims that both districts are equal. So so sometimes it'll say assume the variances are equal in words, but showing you this last part where it says sigma 1 squared equals sigma 2 squared, that's assuming they were equal. If they weren't, you would see the not equal symbol there. So we have a 2-tail test. And then alpha is 0.05. So here are the numbers. So 15 plus 15 minus 2 is 28. So we have a two-tailed, 0.05, 28 degrees of freedom. That's column 4. Two-tailed 0.05, automatically going to be a plus and minus. And there it is, if you can see that moving or not, 2.048. So it's plus and minus 2.048. So our decision rule would be reject the null if t is less than negative 2.048 or if t is greater than positive 2.048. It falls in the middle, fail to reject. All right, so let's kind of go through the calculation here again. So both degrees and both ends are 15, so therefore both n minus 1s would be 14. Here are the standard deviation. So 14 times 2300 squared plus 14 times 2100 squared all over 15 plus 15 minus 2 times 1 over 15 plus 1 over 15, the square root of that. You end up with 804.156. So our test statistic would be 28,900 minus 30,300 divided by 804.156, and you get negative 1.74. Now this one, I showed punching it, like in a regular calculator. I'd be real careful. Yeah, you can't even see this arrow means there's that arrow right there, if you can see it above the box. That means there's more stuff to the right. So that's this square root part right here. You see the 1 right there. That's that first 1 right there. And times the rest of that, and there's the 804.156. And then there's the test statistic. Notice I use parentheses in the numerator. Very important. Anytime you have a big fraction and then you got pluses and minuses on the top or bottom, you would need to use parentheses. All right, so negative 1.74 falls in the middle between those two critical values, which is the fail to reject zone. So we fail to reject that they are equal. So we don't, in other words, we don't have enough evidence to say they are unequal. And here's the two sample. Oh, this I chose, oh wow, okay, I chose the wrong, let me do this again so I can fix this. I chose the wrong hypothesis test. Now, fortunately, the only thing that would affect is the p-value, which we weren't getting, but it would be nice to do it correctly here. The test statistic calculates the same no matter what you do, but absolutely it'll affect, you'll see the difference there. I mean, we're not using a p-value, but you see that 0.926 p-value, that's going to be, although, wait a minute, I take that back because I'm showing equal. You know what, I think, okay, let me just mention this, that I believe I moved it over. I must have moved it over to equal before I hit enter. But still, that does not look good. 28.9. Yeah, so that, let's see. Okay, and the ends are 15. I should know that. And this next one's 30,300. Standard deviation of 2,100. That's 15. Equal. Now, let's see. Okay, I'll do the calculation here in a minute, but let me fix that box at least. Let's get that out of there so I can edit these notes. Cut. Put this in here like so. Now, let's arrow down. Yep, the negative 1.74, and that p-value was right. In fact, you know what, actually I could show you real quick whatever we had it. Hopefully those numbers will stay in there. If they will, okay. I don't remember which one of these two I had it before. Was it that one that was flashing? It doesn't matter. They're going to be the same p-value for either direction of those two, but I'll show you. So you see the p-value is different, 0.463. So I had it correct. I just did not have the right thing visually correct on the left, the first screen. Well, all right, so that takes care. Let me go and save this file. And here's one more example. By now you probably have the hang of this, so probably go through faster this one. Let's see. Television time watching women and men. 14 women, 17 men. At the 5% significance level, do the data provide? This is a typo, not by me. I copied it from somewhere, but CO should be DO. Do the data provide sufficient evidence to conclude that the mean time spent watching television by women is less than that of men? All right, so the women are the first group, men are second group. So we're saying mu1 less than mu2. Okay. Women's time watching less than men's. So that's our claim. Then that makes the null greater than or equal to. Degrees of freedom would be 14 plus 17 minus 2. 29 degrees of freedom. What's our alpha? 5%. Left-tailed, meaning it'll be negative, so it'll be one-tailed on the chart. One-tailed, 5%, 29 degrees of freedom. Next to the bottom, 1.699, but negative 1.699. So we would reject if the t is less than negative 1.699. So we go through this process in the square root, plug all those numbers again, plug this in, you get 1.4839. Then the test statistic would be the first mean, which is 12.9, minus 16.4 divided by 1.4839, which is negative 2.359. Yeah, you see I drew up here, round at negative 2.36. That's good enough. But either way, it's clearly to the left of the negative 1.699, clearly to the left. Therefore, it's absolutely in the rejection region. So it looks like I did the calculator. Input there. This time I have it correct with less than. Pulled yes, that's correct. Got everything in there. And you see there's the negative 2.35, whatever, 8, which we have negative 2.359. That's it. So we got that right. And there I just did it the I don't know what happened over here, but it doesn't match. So I'm getting that. I think it's best just to get that off of there more than it is. Try to explain what happened. Anyway, so be careful if you're doing it manually in a calculator. Oh, I'm sorry, that was right. I was looking at the test statistic. My mistake. Yes, that's the denominator. That's this 1.4839. That's your standard deviation that goes on the bottom. So there, that's what that was. Okay, I was looking at the t-test. Then you would have just, then that's that bottom number right there. So, and that is the end of this video. Oh, well, I may mention that so therefore we reject and we support the claim. So we do feel that the TV time for women is less than that of men. Now that concludes this video.